Welcome to VLearn's online class of MCS-012. In today's session, we will discuss about the instruction set architecture. In instruction set architecture, we will discuss about instruction set characters, instruction set design considerations, addressing elements, instruction set and format design issues, and examples of instruction format. First of all, instruction set characteristics. If we talk about the central processing unit, we all know the work of central processing unit is to perform the calculations, issue the commands, and coordinate all other hardware components and execute programs including the operating system and application programs etc. on the computers. But CPU is primarily the core hardware component, then we must speak to it in the core binary machine language. The words of machine languages are known as instructions on the basis of which the computer system operates, and its syntax is known as instruction set. Instruction set is a boundary where the computer designer and the computer programmers see the same computer from different viewpoints. The computer instruction set provides a functional description of the processor, that is the detailed list of instructions that a processor is capable of processing, or you can say the list of instructions that the processor can process, and the description of the types, location and access methods for the operands. Instruction set is a collection of machine language instructions that a particular processor understands and can execute. Instructions can take different formats. Instruction format basically includes the length of the instruction, the type of the instruction, the length and position of the operation code in an instruction, the number and length of operand addresses, etc. If we talk about an instruction set, for example, if we give A plus B into C, then A, B, C are operands on which particular set of instructions are to be performed. Plus, multiply, minus, these all are instructions, or we can say opcode, or we can also say operators, on the basis of which we can perform set of instructions on the specified operands. There are various elements of instructions. Two major elements are opcode and operand. As I already told you that if we give A plus B, then A and B are operands and plus is opcode, or you can say operator, or you can say the instructions on the basis of which the instruction will be executed. The opcode field or operation code field specifies the operation to be performed. The operands specify where are the operands. It specifies the address field of operand on which the data processing is to be performed. An operand can reside in memory or a processor register, or can be incorporated within the operand field of the instruction as an immediate constant. Therefore, the mode field is needed that specifies the way the operand and its addresses is to be determined. So here we specify the addressing mode to specify the way the operand and its addresses to be determined. You can see in this opcode size is 6 bits. So in general it will have 2 raised to power 6, that is 32 operations total. There are only one operand address machine. There are 2 bits for addressing mode, which specifies the mode of address. Therefore, 2 raised to power 2, that is 4 different addressing modes are possible for this machine. And last field, that is 8 to 31, that is 24 bits. Here is the operand and the address of operand field. Next is instruction set characteristics. Now, if we talk about the instruction set characteristics, Then in instruction set characteristics, the next question is how is an instruction bit represented? Instruction is represented as a sequence of bits, and a layout of an instruction is termed as the instruction format. It is primarily machine dependent, and the CPU instruction set can use many instruction formats at a time. Now, how many instructions are in a computer? A computer can have a large number of instructions and addressing modes. The older computers with the growth of integrated circuit technology have very large and complex set instructions that are also called CISC. We will discuss in the next sessions about CISC and RISC. Now, what are the basic considerations for the instruction set? There are some basic design considerations for the instruction set, that is set of data types. For example, integer, long integer, doubles, characters, strings, etc. Set of operations on those data types. Set of instruction format includes issues like number of addresses, instruction length, etc. A set of techniques for addressing data in memory or in integers or in registers, and the number of registers which can be referenced by an instruction and how they are used. Now, if we talk about the type of the operand, then according to the data type or according to the data the operand is categorized into different categories. We can specify address for the operand, that is operand residing in the memory are specified by their memory address, and operands that resides in registers are specified by the address of their register. The address provided in the instruction are operand reference. Another type is numbers. Number can be integer number, number can be decimal number, or you can say floating point number. Next one is characters. A common form of data is text or character string, and characters are represented in numeric form, mostly in ASCII, that is American Standard Code for Information Interchange. Next one is logical data, that can be either true or false, means each word or byte is treated as a single unit of data, and when an n-bit data unit is considered as consisting of n 1-bit items of data with each item having the value 0 or 1, then they can be viewed as logical data. Now, after discussing about the types of operand, the next is types of instructions. Instructions can be data transfer instructions. Instructions can be data processing instructions. Instructions can be program controlled instruction, or it can be miscellaneous privileged instructions. If we talk about the data transfer instructions, then these instructions transfer data from one location to another in the computer to another location without changing the data content. Some of the most common transfers are from processor registers to memory, processor registers to input output, processor registers themselves. Some of the instructions for data transfer are load, that loads the content from the memory to the register, store, that stores the information from the register to the memory location, move, to transfer the data from one register to another or between the CPU registers in memory, exchange, to swap the information between two registers or a register to a memory used, clear, causes the specified operand to be replaced by 0, and set causes the specified operand to be replaced by 1s. Push, to transfer the data from the processor register to the top of the memory stack, and pop, to transfer data from the top of the stack to the processor register. Next category is data processing instructions. Data processing instructions perform arithmetic and logical operations on the data. The data manipulation instructions can be divided into three basic types, that is arithmetic, which includes addition, subtraction, multiplication, division, etc. Logical, which results in either true and false, that can be and or not, XOR, and shift operations, used for shifting or transferring of bits either to the left or to the right, and it can be used to realize simple arithmetic operations or data communication recognitions, etc. Shifting can be logical left and right shifting, shifting can be arithmetic left and right shifting, or shifting can be circular shift. If we talk about the logical right and logical left shifting, then it inserts 0 to the end bit position and the other bits of the words are shifted to left or right respectively. The end bit position is the leftmost bit for shift right and rightmost bit for the shift left. The bit shifted out is lost. If we talk about the arithmetic shift, in arithmetic shift left and arithmetic shift right are almost same as logical shift left and logical shift right, but the difference is that the sign bit remains unchanged. On the arithmetic shift right, the sign bit is replicated into the bit position to its right, and on the arithmetic shift left, a logical shift left is performed on all the bits but the sign bit which is retained. Next one is circular shift, that is rotate left and rotate right. Bits shifted out at one end of the word are not lost as in the logical shift but are circulated back into the other end. Next is program control instructions. These instructions specify the conditions for altering the sequence of program execution. Generally, the program counter points to the memory location that holds the next instruction to be executed. The change in the value of program counter as a result of execution of control instruction like branch or jump can cause a break in the sequential execution of instructions. Some of the program control instructions are branch and jump, skip and call and return. These are the examples of program control instructions. Next one is miscellaneous and privileged instructions. These instructions contain the instructions for starting and stopping input and output, test input output, and to specify destination as an address, interrupts and state swapping operations, etc. All these instructions comes under the category of miscellaneous and privileged instructions. Now, some basic instruction set characteristics. If we talk about the basic instruction set characteristics, then the operands can be addressed in the memory, registers and input-output device address. The instructions having less number of operand addresses in an instruction may require lesser bits in the instruction. Most of the instructions do not require more than 3 operand addresses, and the type of internal storage of operand in the CPU is the most basic differentiation. Now, in general, the instruction set architecture, that is ISA, of a processor can be differentiated using the 5 categories, that is operand storage in the CPU, that is where are the operands kept other than the memory, number of explicitly named operands, operand locations, operations that can be provided, and type and size of operands. Now, the 3 most common types of ISAs, that is instruction set architectures, are evaluation stack, the operands are implicitly on the top of the stack, accumulator, the operands is implicitly the accumulator, general purpose registers, that is GPR, all operands are explicit either registers of memory, either registers or the memory locations. You can see push A, push B. On the stack machine, if we want to perform C is equal to A plus B, then we can implement it by using push A, push B, then add and pop C. That is load A, add B and store C. You can see register and memory references. On an accumulator machine, we can execute it by load A, that is load memory location A into accumulator, then add B to the accumulator and store value into the memory location C. And if we want to implement on both the architectures, that is register memory and load stored through the register, then the register memory can be implemented by load R1A, that is A's content are loaded to R1 register, B's content are add R1 comma B, it means B content are added with R1 and store C R1, that is R1 content are stored in C. And load store through registers contain load A to R1, B to R2, add R3, R1, R2. It means R1 and R2 are added to the R3 and store the final result, that is in the R3 to the C. The next topic is addressing scheme. Now, what is addressing scheme? It refers to the mechanism employed for specifying the operands. There are a multitude of addressing scheme and instruction formats. The addressing schemes are further divided into immediate addressing scheme, memory reference, which are further divided into memory direct and memory indirect, register reference, that is divided into register and register indirect, displacement addressing, that contains indexed addressing, base addressing and relative addressing, and the last one is stack addressing. Now, what is the use of these different types of addressing? Immediate addressing can be used for moving constants and initialization of variables. If we talk about the immediate addressing, then when an operand is interpreted as an immediate value, it means when an instructions contain the immediate value of the operand, then it is known as immediate addressing. You can see there is instruction load, I for immediate addressing mode, and 7 is the operand value. It means instructions contain the value of the operand. So this is a type of immediate addressing. Direct addressing means the operand field of the instruction specifies the address of the intended operand. In this, you can see these are the memory addresses. This is the instruction that contains load D for direct, and 500 is the operand address, which specifies the address of the main memory from which the operand is to be fetched. It means on evaluating this, 500 is the address, the control will goes to the address, so that is 500, and from this address the value will be fetched. This is direct addressing, in which the instruction contains the address from which we can access the value. If we call indirect addressing, indirect addressing means the instruction contains the address which contains another address from which the operand can be fetched. You can see the operand field of instruction specifies the address of intended operand, that is if the instruction load 500 uses indirect addressing scheme. That means 500 is an address which contains another address, that is 50A, and on 50A we will find the value of the operand. This is direct addressing and indirect addressing in case of memory addressing. If we talk about the register addressing, register addressing means when the operands are taken from the registers implicitly or explicitly, then it is called register addressing, and the operands are called register operands. If the operands are from memory locations, then they are called memory operand. Register addressing is frequently used for storing local variables of procedure or for holding pointers to structure in the programming languages. Now, register addressing is further categorized into register direct or register indirect. Register direct means in which the instruction contains the address of the register from which the value is to be fetched, and indirect register addressing means in which the operand specified a register that contains the address of the operand. In this, it contains the address of the operand that is stored in the memory, and the address capability of register indirect addressing scheme is determined by the size of the register. next one is indexed addressing scheme. Indexed addressing scheme is a type of displacement addressing. It is basically used to access the memory of an array. In index addressing scheme, the operand field of the instruction contains an address and an index register which contains an offset. And this addressing scheme is generally used to address the consecutive locations of the memory. The index register is a special CPU register that contains an index value, and the contents of the operand field A is taken to be the address of the initial or the reference location, or you can say the first element of the array. The index register specifies the distance between the starting address and the address of the operand. So, effective address can be achieved by adding the address of the initial or the reference location plus the address of the index register in case of indexed addressing. Next is base register addressing, an addressing scheme in which the content of the instruction specifies base register is added to the displacement field or the address field of the instruction. That is, the content of an instruction specify the base register. The base register is added to the displacement field or address field of the instruction. If we talk about the relative addressing, then the register R is a program counter containing the address of the current instruction being executed. The operand field A contains the displacement of the instruction or data with respect to the current instruction. This addressing scheme has advantages if the memory references are nearer to the current instruction being executed. After the displacement addressing, the next one is stack addressing. In this addressing scheme, the operand is implied as top of the stack. It is not explicit but implied. It uses the CPU register called stack pointer, which points to the top of the stack, that is, to the memory location where the last value was pushed. A stack provides a sort of indirect addressing and indexed addressing, and this is not a very common addressing scheme. Now, what are the instruction set in format design issues? Some of the basic issues of concerns for instruction set designs are completeness and orthogonal. Completeness means the primary concern is that the instruction set should be complete, which means there is no missing functionality. If we talk about orthogonal, the second concern is that the instruction to be orthogonal, that is, not unnecessary redundancy should be there. For example, integer operation and floating number operation usually are not considered as redundant, but different addressing modes may be redundant when there are more instructions than the necessary because the computer takes longer to decode. The instruction set in formal design issues also contains the instruction list. Now, what is the significance? It is a basic issue of format design. It determines the richness and flexibility of the machine and basic trade-offs, that is smaller instruction versus desire for more powerful instruction. Normally, the programmer desires more opcode and operand as it results in smaller programs and more addressing modes for greater flexibility in implementing the functions like table manipulation, multiple branching, etc. Now, what are the factors that are to be considered for deciding about the instruction length? There are various factors that are to be considered for deciding about the instruction length, that are, first is memory size. If larger memory size is to be addressed, then the more bits may be required in address field. The memory organization, that is, if the addressed memory is virtual memory, then the memory range which is to be addressed by the instruction is larger than the physical memory size. Then next is memory transfer length, that is instruction length should primarily be equal to the data bus length or multiple of it. And next one is memory transfer, the data transfer rate from the memory ideally should be equal to the processor speed. Now, while allocating the bits among opcode and operand, what are the main points that are to be, main factors that are to be considered? First is number of addressing mode. The more are the explicit addressing mode, the more bits are needed for mode selection. However, some machines are implicit modes of addressing. Next is number of operands. Fewer number of operand references in an instruction, although require less bits, yet result in longer programs. Then register addressing versus memory addresses. The register references require few bits in comparison to the memory addresses, and granularity of the address as far as memory references are concerned, granularity implies whether an address is referencing a byte or a word at a time. This is more relevant for machines which have 16-bit, 32 bits and higher bit words. Next one is variable length instruction. The designers came up with the idea of having a variety of instruction formats of different length. Now, there are various advantages of such a scheme, that is, large number of operations can be provided which can have different length of instructions, and it provides a flexibility in addressing schemes to effectively and efficiently and compactly use it. So, this is all about the variable length instructions and instruction set characteristics, instruction set design considerations, that is operand data type, types of instruction and number of addresses in an instruction, different addressing schemes and instruction set and format design issues. That's all for this session. Thank you.